In this lesson, we'll be talking about infinite limits. Infinite limits is something that we've hinted at a few times already. Namely, we took a limit where the limit just shot up towards infinity. It shot up without bounds, and we said, well, the limit does not exist, but technically we could call this infinity. We've also looked at examples of an infinite discontinuity, where the function went up without bound, and we said, okay, well, this is an infinite discontinuity. Let's go through this concept of formally saying, well, what does it mean for a limit to be infinite or not? We're looking at the limit as x approaches 3 of 1 over x minus 3. This graph has a vertical asymptote at 3, and it looks a lot like the graph of 1 over x in that on the right and above it goes towards positive infinity and towards 0 on the right, and on the left it looks something similar. So here's what's going on. On the right side of the limit we've got trending towards infinity, and on the left we've got trending towards negative infinity. We can say immediately this limit does not exist because the left and right hand limits appear to be doing something different. But it's right there. The graph is trending towards infinity and the graph is trending towards negative infinity. Let's see if we can work on this a little bit further. Here's an official definition. We say that the limit as x approaches c of the function equals infinity, and this is our official definition. You pick some sort of bound m greater than 0, and that's just saying a certain value that's large enough that I'm claiming the function can get above that value. I pick this value, and if the function's going towards infinity, you can always find a small enough interval so that if x is in this interval, then the overall function is higher than that upper bound. Pick an even higher upper bound, you might need a smaller delta. It's similar to this epsilon delta stuff we did before, but now this time we're just saying pick a large number, and I claim there's a way to pick a small enough interval of values that it lies above that large value. Similarly, you can pick a very negative number and do the same. We can also talk about left and right hand limits using these replacements. And so let's just see what this means in the context of our problems. Evaluate the limit as x approaches 3 from the left of that function and from the right of that function. Let's go back a slide. At 3 from the right, we said it was trending towards infinity. This fits the definition. If I pick some large enough number, I can find a small enough interval of x values that lie above that. Similarly down here, if I pick a very negative number, I can find a small enough interval of x values that all lie below that. Sure enough, based on these definitions, we can say negative infinity and infinity. So from the left it's negative infinity, from the right it's positive infinity. And really we don't have to think of these in terms of the official definition. Just if it's trending towards infinity, we call the limit infinity. If it's trending towards negative infinity, we call the limit negative infinity. Now, these limits still technically do not exist, but this is a new thing we can write if it does turn out to be infinity or negative infinity. What we're going to do with this first off is officially define a vertical asymptote differently than what you did in college algebra. Simply enough, if x approaches infinity or negative infinity from either direction, we call that a vertical asymptote. It's a trend of infinity in the graph itself. Here's a theorem, and this is what you probably used in college algebra. If you've got the numerator being non-zero and the denominator being 0 when you plug in a certain value, then there is a vertical asymptote at that point. Remember, 0 over 0 could be anything, but a non-zero over 0 turns out to always be a vertical asymptote. Specifically, the limit is always something infinite, which is kind of nice to know. Division by 0 is actually some form of infinity. The only other thing is that you do need to require that the function is defined somewhere around there for this to make sense. Anyway, find the vertical asymptotes. We discovered that the limit of this to the right was infinity, so x equals 3 is certainly an asymptote. And we can just look at it as, hey, this number on top is not 0, but at x equals 3, the number is 0. 1 over 0 is a case where we're going to get a vertical asymptote. Let's look at this. When the denominator is 0, I get x squared equals 4, and so x equals plus or minus 2. With that said, at plus or minus 2, the numerator is not 0, so my vertical asymptotes are at x equals 2 and x equals negative 2. This really is just plug in the values that make the denominator 0, and if the numerator is not 0, that's a vertical asymptote. Next one, let's factor this first. We get, let's see, how about x minus 5, x plus 2 over x plus 2, x minus 2. Now we can pretty well see that if x is negative 2, then we have a 0 in the numerator and a 0 in the denominator. That is not a vertical asymptote, that's a hole in the graph. So with that said, if we cancel these out, then we may get a vertical asymptote elsewhere. If you recall the rule from your college algebra class, it probably was something like it's the zeros of the denominator after simplifying. With that said, the only vertical asymptote is at x equals 2. Next one. Tangent of x, if you remember from your pre-calc class, is sine x over cosine x. Wherever the denominator is 0 and the numerator is not, is a vertical asymptote. It turns out that the sine of x and the cosine of x are never 0 at the same time. So we really just look at where cosine x equals 0 gives a vertical asymptote. This happens at every odd multiple of pi over 2. This is, say, pi over 2, 3 pi over 2, 5 pi over 2, and so on, as well as negative pi over 2, negative 3 pi over 2, and so on. These are the values where the cosine of x is 0, and I would point out also that the sine function is either 1 or negative 1 at all of these points, so we will always get a vertical asymptote out of that. Let's go back to limits. How do we calculate these limits whenever we're talking about infinity? This is what we do. We do some sort of substitution. We've got 1 squared minus 3 times 1 is negative 2. When I plug it into the denominator, I get 0. So what I do is I keep the symbol that I was using. This was a left-hand limit, and so it's still a left-hand limit. The denominator is approaching 0 from the left, meaning it's approaching from negative values. Thus, all these numbers are negative, all these numbers are negative, and so all you really have to say is I know it's going to be infinity, decide whether it's positive or negative. A negative over a negative is positive. Next one. Same problem, but now we're looking at 1 from the right. So we still get negative 2, but now we're approaching 0 from the right. So the values that are approaching 0 are always a negative over a positive. Consequently, this is going to be negative infinity. So that's the trick. Plug in the values, maintain the symbol. Sometimes it doesn't make any sense if there's not a symbol. So if we weren't looking at it for a left and a right, you might have to check both the left and the right and make sure that they're the same. Either way, as soon as you get the 0 in the denominator and a non-zero in the numerator, just figure out the sign of these values, and then that's the type of infinity for your answer. So here's a little bit of infinite arithmetic that we can use that's kind of helpful. Let's look at the setup where f of x has a limit of infinity and g of x has a finite limit, some L here. Don't know what the value is, we'll talk about it in each of the contexts. If you take an infinite limit and add or subtract a finite value, it's still infinity. If you take an infinite limit and multiply by a finite value, it's also still infinity. The idea is that if you multiply by a positive value, you get positive infinity. By a negative value, you get negative infinity. Unofficially, you could say something like infinity plus a number is infinity. Infinity minus a number is infinity. Infinity times a positive number is infinity. And infinity times a negative number is negative infinity. Finally, remember g of x is a finite number. If you take any number and divide by quote-unquote infinity, you get 0. These are what we call infinite arithmetic, but we normally don't ever write infinity times something or infinity plus something or infinity divided by something or something divided by infinity. However, whenever we do these, we can always write it down with these particular rules. I will say these properties hold for also negative infinity. They also hold for left and right hand limits. They're all pretty similar. What you expect to happen seems to happen. Let's do a couple. First off, we've got the limit as x approaches 0. What I see here is this part is going towards, well, x is going to be 0, and this is 0 regardless. It could be 0 from the left or right because it's x squared. We're going to get 0 either way. 1 over 0 from the right, because it was squared, it's coming from the right regardless, is going to equal positive infinity. So I have 1 minus the idea of infinity. That's going to be negative infinity. It's kind of like negative infinity. When you add a 1 to it, it doesn't make any difference. Now this is the correct notation here. Notice I did not write 1 minus infinity. That doesn't make any sense to write. What I did do though is I wrote off to the side what the value was, and then I just wrote my final answer of negative infinity. Next one. X approaches pi over 2 from the left. So you probably need to know a little bit about the tangent function. Tangent function has asymptotes at all the odd multiples of pi over 2, which we talked about just a moment ago. What it looks like, put negative pi over 2 on here also. What it looks like is this kind of wave here. Crosses in the middle of the interval and has a bit of rotational symmetry also. But you'll notice as x approaches pi over 2 from the left, the function is approaching infinity. So this is approaching infinity. Therefore, we've got pi over 2 squared plus 1 is a finite number. A finite number divided by something getting infinite is 0. So division by something infinite is always 0. Unofficially, you could say a number over infinity equals 0, but we don't write that. 4 cosecant x. So let me just go ahead and rewrite this as 4 over sine x. Remember, cosecant x is 1 over sine x. And so the graph of sine x looks something like this. As x approaches 0 from the right, the function is approaching 0 from the positive side. So this is 4 over 0 from the right. You'll notice they're both positive, so this is infinity. Next one. X is approaching 0 from the left. If you recall the graph of 1 over x, something like this, and as x approaches 0 from the left, we're getting 1 over 0 from the left, which should be negative infinity. 3 times 0, which is 0, so it's a finite number plus the negative infinity concept. I know my answer is negative infinity. Again, I did not write 0 minus infinity, I just wrote negative infinity. I was thinking about it, but I did not write it because there is a notation issue here.